Welcome, everyone. Thanks for being here for today's Rubin Science Assembly. Today, we're going to have a presentation from the Pitt-Google broker after just a few announcements and a brief introduction. For our announcements, as of February 24th, alerts are now publicly available. You can learn more at these two websites. We have our For Scientists page and then also our prompt products documentation. There's also a press release all about the Rubin Observatory first alerts, so you can learn more. I'm going to pop the link to these slides in the chat so that you can get to all the links that you're going to see on these announcement slides. Other announcements, the Rubin Data Academy is coming up in June. It's going to be the week after the summer AAS. This is a fully virtual week of all tutorials. It's kind of designed to get students started on their summer projects with Rubin Data. Later in the summer, July 27th to 31st will be the Rubin Community Workshop. We're back at SLAC in Menlo Park this year. The forms for abstracts and session suggestions are now open. Registration is also open. And you can find that all on the RCW website. Looking forward to the upcoming Rubin Science Assemblies. Next week, we'll have a presentation from the Points of Interest broker. Then we'll hear about the Ample broker. The following week, April 23rd, will be a presentation from Gemini Observatory about their follow-up resources. And then right at the end of April, we'll hear from the SNAPS broker, which is the solar system broker. And from there, assemblies will continue on a weekly basis. We will continue alternating between drop-in sessions and presentations and tutorials. Another reminder that there is a current job opening with the Link Frameworks. They're hiring a system software engineer. This would be located at Carnegie Mellon. There was no deadline in the announcement. They just said applications are reviewed on a rolling basis. So check there for more information about that job. And also as a reminder, there's a new call for proposals for Rubin and /LSST compute resources. The deadline is coming up pretty soon. It's April 6th. This call is going through like the same mechanism as time allocation proposals do for Noir Lab, but it's not for telescope time, it's for compute time. So this is to ask for batch compute and GPU resources for Rubin-related data processing. You can ask for limited term data storage for any large files for inputs or that might come out of your processing, maybe that you want to share with everyone. So do take a look at that if you want to do some like bigger processing with Rubin data. As always, the reminder slide that you have a users committee and they are always eager to hear from you feedback about the Rubin data products and services and tools for accessing and analyzing those data products. And the usual reminder that the Link Frameworks hosts office hours, and they're the hour immediately after the Rubin Science Assembly. It's either a drop-in session or sometimes they're doing a tech talk, so you can learn more about their resources. All right, so all of those slides and all the links in them are in the chat. I'll just repost for people who might have just joined us. And now just a really brief primer for alerts and brokers. Of all the data products that Rubin Observatory will make, there will be the annual data releases that come out sort of on a yearly basis that reprocess everything we've ever obtained. But then on a shorter time scale, we have the prompt products coming out. Those come out, the alerts are one of the prompt products, and they are notifications of sky changes that come out within minutes of a new image being acquired. The same data that gets streamed as alerts appears in catalogs that are accessible and queryable within 24 hours. And then the images, raw and processed images that the alerts and the catalogs are based on, they are subject to an 80-hour embargo, but then they become available to data rights holders after that. For the alerts themselves, these notifications of detected sky changes, we expect up to about 7 million alerts per night once we have the full set of templates over the full sky, and like every new image is creating and transmitting alerts. And so alerts and brokers together are kind of like a community fountain that everyone can go to and drink from, do science from. When I say an alert is a notification of a sky change, this is what's actually happening. A new science image comes in. You take a template that you made from images acquired like last year, you subtract the template from the science frame to make a difference image. Then you do source detection on that difference image. And every source that you detect, positive or negative, so long as it has a signal to noise ratio greater than 5, it becomes detected and an alert is produced for that particular source in the difference image. The alert itself is just a machine readable file that contains data for the detected source, so sky location like coordinates, measurements like magnitude, shape, and size, metadata, the date, the time, the filter, 12-month history of past detections, and very small image cutouts of the science template and difference images. Alerts are a completely public data product. They aren't something that goes to individual users. The alerts are streamed to brokers, and these brokers are independent software systems that process and serve alerts to the science community. They add value to the alerts, so they filter them, they can calculate additional properties, they do cross-matching with other catalogs, and then they also offer the data access services, usually a web-based user interface or an API, so that you can get at the alerts through the broker. You can find an overview of alerts and brokers on the Rubin Observatory for Scientists website. There are 9 in total. 7 we call full stream because they accept the full stream from Rubin Observatory. 2 of the brokers we call downstream. They have more specific science focus, so they don't need all of the alerts. They only need ones that sort of match with their science goals, and so we call them downstream brokers because usually they take a subset of the stream from one of the full stream brokers. And that is it. That's all the announcements and the brief primer to alerts and brokers. Today, it's the Pitt-Google broker, so I'm going to hand it over to Chris, who is here to take you through all about Pitt-Google. Chris, welcome. I'm going to stop sharing and let you share screen. I'll let you introduce yourself and the team and basically take it away.
Great. Thank you very much. Let me go ahead and set this up. Hi everyone. My name is Chris Hernandez. I'm currently a graduate student at the University of Pittsburgh, and I'm the lead developer for the Pitt-Google Alert Broker. And so my goal for today's session is to give an introduction on who we are, what we do, and how users can interact with the data products that we serve, whether that's through our Python library or an additional interface that we have through Google Cloud Platform. And I'll start off today's session with a brief overview of our architecture. So maybe I'll start off with the name Pitt-Google. And the term Google in the name Pitt-Google actually just reflects our adoption of Google Cloud Services as a solution to some of the challenges our field is currently facing, especially in the era of the Verisi Rubin Observatory. So we use a number of different Google Cloud services to be able to process and distribute various alert streams, whether that is the original alert stream that we ingest from the survey or the value-added data products that we then distribute to the global community. I like to compartmentalize our architecture into 3 modules, these being outlined in the diagram on the left. So we have a number of services that are dedicated specifically to alert ingestion. Once those alerts are ingested, we then have a number of services that process the alerts in real time. We have seen latencies of order milliseconds to seconds. So when I say real time, I do quite literally mean real time. And then finally, we have a series of services dedicated to storage of the alerts as well as the classifications that we make. And the products or the services that we use to enable all of this are outlined in the bullet points. So Google Cloud PubSub is a publisher subscriber service. I'll get into more of the details for all of these services in the next couple of slides, but I'll just outline them here briefly. The Google Cloud Storage buckets are basically a cloud bucket that we have that hosts all of the original Avro files for LSST. And that's also true of all of the other alerts that we ingest from other surveys, though the format depends on the format the survey uses to distribute the alert itself. Um, BigQuery is a optimized analytic data warehouse, which we use to store all of the original alert data, excluding the cutouts, in addition to any value added information, i.e. classifications. And finally, Google Cloud Run is essentially a scalable service used to process message requests. In this case, by message request, I just mean a single alert. Um, and finally, for a good portion of today's session, I'm going to be highlighting our Python library, which is the Pitt-Google client. This is a method that users can use to interact with the data products that we serve. So, as you may be aware, we are currently ingesting, processing, and distributing alerts from LSST. But we have a number of additional surveys whose alerts we process and distribute as well. We've been processing ZTF alerts since late 2020, and within the past year have also integrated pipelines to receive and process alerts from LIGO Virgo Kagra. And within the past month, I've integrated a number, or actually all of the tables from Gaia DR3 to enable cross-matching, both in real time and also not in real time. Okay. I will dedicate some time to talk about the ways I have structured certain services for our broker to be able to optimize the amount of data that a user interacts with. We are living in this era of big data within the field of astronomy. And so one of the solutions to address the challenges that we will face are HealPix pixels. If you're unfamiliar with HealPix, it's essentially a method used to partition or segment a curved surface. And so in this case, we can imagine the celestial sphere being partitioned into different segments. And so depending on the order of the HealPix value, you can either increase or decrease the resolution of a given region of the sky that you're interested in observing or interacting with the data associated with that region of the sky. And so that's demonstrated on the diagram to the left. As you increase the HealPix order, you're basically increasing the resolution. And so each of these pixels or quadrilaterals that you're seeing in the diagram have equal areas. So all of these pixels are equal in area, and the same is true of the other orders demonstrated here. All of this really to say that if you're interested in filtering alerts based on spatial positions or querying specific classes of objects at a given position, all of that is facilitated with the fact that we include HealPix pixels in the metadata of outgoing alerts that we publish and distribute to the community. And I promise to touch on this in the next couple of slides. Diving into the services that I mentioned on the first slide, we again use PubSub as a service to distribute information. What this basically means is that users can subscribe to the topics that are on the screen here. But I think the utility in doing this is that you can actually subscribe to various different points in our pipeline. So the diagram here at the top, this is the module dedicated to alert ingestion. So let's say you're interested in interacting with the full LSST alert stream. Well, then you can directly subscribe to that topic and receive information, all of the information embedded within the alerts. Let's say, for example, you're interested in identifying extragalactic transients. and let's say you're interested in type 1a supernovae, well, then you can, directly subscribe to the relevant topic, which would likely be LSST supernova, to receive information about the classifications that our module basically incorporates to the alert data. So not only will you access information about the alert, but you'll also have information about the classification that we've added on top of the alert information. Um, I'll note here that we have a number of loop streams. So you can essentially replace the survey, in this case LSST, with any of the other surveys that we serve data. So, you can change this to ZTF, LBK, etc. This loop stream is more of a developer environment in the sense that messages published to this loop stream are published at a rate of one alert or one message per second. That way you can check to see whether your filter, do you wish to use one, validate successfully, or let's say you're interested in deploying an application to analyze the alert stream in real time. You'll likely want to subscribe to this loop stream to make sure that your application works as you intend it to. I'll quickly note here that we have a number of value-added streams. We currently have 3 modules in production. That number is increasing as we speak. So we have 2 machine learning. We have 2 classifiers, basically super and nova and upsilon. Upsilon is a multi-class classifier that identifies subclasses of variable stars, and super nova is trained to identify likely type 1a supernova candidates. And so this is just a binary classifier. And then lastly, we have a variability module. This is essentially identifying or calculating useful statistical features to identify real varying sources. And if you have any questions, I'm happy to chat a little bit more about that. Moving forward to Cloud Run, as I mentioned, this is a scalable service that we use to containerize an application, deploy that application to the cloud, and be able to perform real-time analysis of the LSST alert stream. I think one of the very interesting things that users can do with our broker is, not only do you have direct access to the alert streams and value-added streams, but if you wish to do so, you could develop your own code to analyze the alert stream in real time. Whether or not you want to do that in conjunction with our team, you are at the liberty to do whatever you would like to do. But I think that using services like Google Cloud Run reduces the barrier to entry for users to be able to analyze data in real time as well. So let's see, I'll skip through this. BigQuery, as I mentioned, is an analytical data warehouse. Users can directly query all of the tables, and you can also perform join statements through the queries. So you have access to all of the information that our broker provides. And I promised that I would go back to heel picks, and here we are. So what we're looking at here is what a unstructured table would look like, meaning information is inserted into the table as it comes in. And if you don't have, I guess if you have a table that is structured in this method, you may know that performing queries against this table can be computationally expensive because depending on the fields that you're selecting, the query has to actually look through each individual row to see whether or not it satisfies the conditions that you've specified in the query. So in order to minimize the amount of data that's read by users, I've incorporated um, two methods, basically clustering and partitioning. Um, Let me move to the next slide here. Um, so in this next slide, I'm showing what it would look like to cluster the table by heel pix order 9 pixels. And so as you can see in this column, rows in the table that have the same value are clustered together, meaning the data is actually sorted based on the values in this column. Um, and if you're interested in a particular region of the sky, well, you can pre-compute the value of that heel pixel and specify that in your query. So rather than reading every single row in the table, you're actually just going to read whatever matches the condition that you specified. So to give an example, let's say we have hundreds of gigabytes worth of data in the table, and you were to specify, Philpix 9. Instead of reading hundreds of gigabytes worth of data in a single query, you could actually read up to kilobytes or megabytes worth of data. So as the number of alerts received by broker increases, this becomes more and more useful to minimize the amount of data read in a query. To further optimize this, we've partitioned our tables by the published timestamp that we received by Rubin Observatory. So you're further increasing, I guess, the resolution at which you perform your queries by specifying both a spatial position and a time range. That can be either a particular date or a time range, a week, a month, and of course, if you're interested in all of the all of the data in the table, well then you don't really need to specify the Kafka published timestamp. But all of this to say, I guess this is just a visual representation of the work that's been done to be able to address challenges in big data. And so for this slideshow, I just want to give a quick shout out to all of the members who have made Pitt-Google what it is today. And so thank you to them. I can quit the presentation here. I'll maybe briefly stop for questions before moving on to the next portion of the presentation. Does anyone have any questions so far? Okay, I will move forward then. Okay, so what you see here, and I will provide a link to this in the chat. This is documentation, a page dedicated to documenting the Pitt-Google client. It contains a lot of useful information about the data products that we serve, as well as links to our user demo GitHub repo. Given that this meeting is recorded, I will walk through the steps that users need to take in order to access the data that we serve. If we go over here to the tab on the left and click on one-time setup, there are a number of instructions that will walk you through this process. I do recommend using a Conda environment to install the Pitt-Google client. So you can, open up a terminal session and go ahead and copy and paste the code that we have available here. All that is required in this process is actually just an email account. We have run into circumstances in the recent past where users start off with using an email affiliated with a university. And oftentimes, if your university has Google Cloud Platform disabled, you're unable to set up the account. So I might recommend using a personal email address first to address that issue. And if you run into more issues, please just reach out to me and we can figure things out. Um, but let me go ahead and walk you through this tutorial. So by clicking on the link, oh my goodness, that is not what I wanted to do. This is what, yeah. Okay. If you click on this link, you'll be taken to the Google Cloud Platform page. Here you're just seeing, the different projects that we have. Your page should be blank. And the steps that you would do is basically click on create a project. You can provide any name to this project. So I'll just say RSA for Rubin Science Assemblies, and then test. I'll go ahead and create the project, and then that'll take just a couple of seconds. And where did that show up? Okay, well, we'll get that in just a sec. Okay, we'll create the project. Keep keep a note of the name of the project that you provide. This next step is the most involved step. So I've gone over and clicked to set up authentication. This process will result in you downloading a JSON key that you use to basically authenticate your email address with your Google Cloud project. And then that way, when you use the Pitt-Google client, you're interacting with your project that you've created. So I do recommend creating a service account. Go ahead and back here on the platform, you can click this little hamburger on the top left and go to I am an admin. You can also alternatively use the search bar and type in I am an admin. So I'll go back here. I am an admin. I will go to service accounts and I'll select my project. The other project didn't show up. Let me try this one more time. RSA, RSA 1. Okay. So now I'm assigned into this Google Cloud project. This is what your page should look like when you click on service accounts. You'll click create service account, type in an ID. So I'll do RSA service account. Click create and continue. And for role, you'll want to select owner and then click done. Now you'll see the service account listed here. In order to download the key, you'll click on the 3 vertical dots, select manage keys, select add key, create new key, and then we want JSON, we'll click create. And so now the private key has been saved to my local device. The last step is to set environment variables. So it would be, opening up the terminal session, copying and pasting the code here, noting that you have to update the values in the string to your Google Cloud project. And here, this environment variable, Google application credentials, is simply the full path to the key that we've just downloaded. To facilitate, logging into this account, you can use this code to have the authentication be performed every time you activate the content environment, and then it'll be deactivated when you deactivate the Conda environment. So this is all of the steps needed to basically interact with the data products that we serve. The last thing to note maybe is I recommend enabling the APIs. So the common products that I mentioned are PubSub, BigQuery, and cloud storage. With that out of the way, I'd like to dive into some demonstrations here, in particular, interacting with Google Cloud PubSub and our BigQuery tables. So I've had a number of conversations with individuals who are interested in accessing the LSST alert stream with filters in place. This process is actually extremely straightforward. There are two methods that I recommend using for creating a filter with PubSub. There are ways to filter based on attributes. Here, the term attribute just means metadata. And so things like DIA object ID, solar system object ID, RA, deck, classification, heel picks, all of this is metadata that we as a broker incorporate to every single message. And so you can create filters to only acknowledge alerts that fall within your defined filter. So to take advantage of heel picks pixels, I'll start off with a filter using spatial coordinates. So let's say you're interested in receiving alerts for a particular region of the sky, or you know an object's position in the sky, and you want to receive alerts that fall within a predefined radius of the location of that object. Well, you would go ahead and import Pitt-Google as well as HeelPix Geom. And in this cell here, let me go ahead and import this. In this cell here, I'm defining a coordinate, meaning RA and deck of a position that I'm interested in receiving alerts that fall within a predefined cone. Here, I'll also specify a radius. Now, in order to filter based on HeelPix values, I essentially want to create a list of HeelPix pixels to define this filter. So as we see here, the output of the cone is a list of 2 HeelPix pixels with values shown here. I've defined the attribute filter as such. So let's take a quick look at the output here. I'm basically saying acknowledge all of the alerts who have attributes with key name HeelPix9, whose value is the 2 pixels that we defined in this cell. One of the things to note here is that the attributes or metadata are strings. So if you want to do integer or float comparison, you can't do that with this method, but you can with the method I'll show after this. Okay, here I've defined the attribute filter. In order to create a subscription, all I have to do is define a topic. So let's say you're interested in, first testing this out, you would define the LSST loop topic. If you wanted this to be the full alert stream, then you would just replace this to LSST alerts. The project ID here is the project ID of the Pitt-Google broker. So all this means is this topic is housed by our Google Cloud project. Here we'll define the subscription. You'll provide a name for your subscription, define the topic that you want to subscribe to, and then schema name here just specifies the survey that it's associated with. So in this case, it's LSST. And then all you have to do to create the subscription is call the method subscription.touch, or I guess the method is just touch. And as a keyword argument, you can provide the filter that we've defined here. Alternatively, let's say rather than providing a filter based on some spatial region, you're interested in only obtaining alerts associated with a specific object. Well, then, if you know the object ID that LSST has assigned to that object, you can simply define it in the attribute as done here. So what this filter does is it checks the attributes of each message. It checks for the key, which is DIA object underscore DIA object ID, and checks whether or not it has this value. And so very similarly, if you're interested in making this watch list, you'll just provide the subscription object, define a new name, and then create the subscription here. I did say that I was going to mention another method which does like integer or float comparison. I don't have that in that notebook that I was just showing you, but that is documented in our Pitt-Google user demos repo. So this is the GitHub repo. If we go into the directory, PubSub, you can scroll down to this other method, which involves user-defined functions using JavaScript. It's a more powerful version of the attribute-based filter because it can operate on the attributes themselves in addition to the full message payload of an alert. So in a very similar fashion, you would define the topic. Here, you would define a JavaScript function. The function that I'm showing here basically checks to see whether or not the number of previous detections for a given object is greater than 20. If that threshold is met, then my subscription will acknowledge the message. If the threshold is not met, then the subscription will simply drop the message. The thing to note here is that this is a different keyword argument than what I showed in the notebook. So just keep that in mind when creating this subscription. I have two more notebooks that I'll briefly go over and then take questions if anyone has any questions. Recently, someone reached out to me who was interested in obtaining photometric information of solar system objects. So this demonstration will show you how to interact with our BigQuery tables. If you're familiar with how the LSST alert schema works, you may know that solar system objects are assigned a solar system object ID in addition to a DIA object ID. And so in the query that you'll see here, we're going to take advantage of that fact. So in order to obtain the available photometry, I'm going to compose an SQL query. I am essentially requiring these fields to be returned based on the conditions I've set. So here I want to receive the PSF flux and its associated uncertainties, as well as the solar system object ID associated with an alert, the band, the MJD value, as well as reliability. You can think of the field reliability as a real bogus score. So if for some reason the image subtraction from the DIA pipeline was contaminated by a cosmic ray or something else happened, it would have a lower reliability score. And so the values of reliability range from 0 to 1. And so this may help you, if you're interested in taking a look at the light curve, to require points in the light curve that meet, a threshold with the reliability score. So in this query, in order to identify solar system objects, I'm requiring the solar system object ID value be not null. And then I'll order the output by solar system object ID. and limit the output to 500,000 rows. As you can see, running or executing the query is straightforward, and then outputting the results. This is a data frame object that you can directly work with on your local device. The results of the query above returned, less than 2,000 unique solar system objects. If you were to remove this limit, that number may be or is likely more than what is quoted here. And also to inspect the light curves, I've provided this function here that takes as input the unique solar system object ID, as well as the data frame object, which in this case is just the result of this query. And here I have a couple of examples. So I've simply taken the object ID from the results of the query and then provided additionally the full data frame object. And this plots a multi-band light curve for all of the points associated with this object. And here's just a couple of more examples of different light curves for solar system objects detected thus far. If you're interested in different kinds of transients, for example, type 1a supernova, you can imagine updating the values in this query to draw from our classification table. You could specify likely type 1a supernova by specifying, probabilities greater than 90%. And if you include these fields, but just update, this field to DIA source, DIA object ID, well, then you would return likely type 1a candidates, and you can similarly inspect the light curves of these objects with the format provided here. Okay, and then lastly, I have a quick demo involving querying both the alerts table as well as our value added table, in this case, our type 1a supernova classifications table. Recently, I've had discussions with a number of individuals who are interested in exploring how the classifications that brokers provide to an individual object evolves as the number of data points increases. And so this query basically returns relevant fields to explore that scientific question. So what I've done here is join two tables, as I mentioned, supernova classifications table, in addition to the alerts table. I am joining the two tables based on the DIA source ID assigned to each alert. And also because we're interested in extragalactic transients, I've specified specific observation reason values that are provided in the alert packet to look specifically for alerts associated or produced by observations in the deep drilling fields. And again, here I've provided a threshold for the reliability score, and then organize the results by observation reason, DIA object ID, and MJD. And so this is what the output looks like. And again, if you're interested in exploring the light curves of these objects, you're able to do so. I think this is a good point to stop and ask if anyone has any questions. Okay, I see a question in the chat. I'll read it out loud. I'm an independent amateur astronomer exploring Rubin alerts, currently using Think. I already run a small project on Google Cloud, so I'm familiar with the costs. If I start using the Pitt-Google broker, would all usage be billed to my own GCP account, or are there free/community supported options available for individual users? This is a great question. So Google by default actually offers a number of free tiers for the services that I've discussed in this presentation. So specific to BigQuery, every individual has the ability to process up to a terabyte's worth of data in a query every single month. And so that automatically renews every single month. Um, I do not recommend providing any, billing information to your account and just letting yourself use all of the free resources until you exceed the quota limit. And then that will, you know, depending on on what you're interested in doing, there are ways to continue using the free tiers. If it so happens that you exceed that quota and your science case um, requires you to use resources, you will be billed for that. But in conversations that I've had with my PI, who is Michael Woodvasey, please reach out to us because we don't want that to be a barrier for individuals to work with our broker or work with GCP. And oftentimes well, the majority of the time, we are actually open to incorporating whether it be like a classifier, a filter, et cetera, into our own pipelines so that we would incur the costs and you would not incur the costs. So to make a long story short, there are free tiers. Um, Feel free to reach out to us and we can go from there. And I see your response to that question. Yes. Any other questions?
Chris, I was perusing the documentation, trying to find the links to the tutorials that you just showed. Probably you showed where they were when you started. Could you maybe show again or put a link in the chat?
Absolutely. Let me do both here. So I've just provided a link to the demos page. Let me go ahead and share my screen real quick.
Yeah.
So if we go to the documentation for the Pitt-Google client, okay, so this is the homepage. You can find the link to the Pitt-Google user demos in this first paragraph. So if we click on that, it'll take you to the repo.
Thank you.
I see someone has their hand raised.
Hi, Christopher. Can you hear me?
Yes, hi there.
Hi. So I was wondering, can you go back in the part where you show us how to use the RA and DAC part, please, for the
Absolutely.
coordinates? If I'm not wrong, you showed us an example with just a single object, right?
Correct.
So if I want to use for a query of objects, let's say about 500. Can I build a loop? Do I need to put like a timer between each object so it won't bug or anything? How can I do this part?
Am I understanding your question correctly? Let's say you want to do something similar to this, but you have a greater a number of objects greater than one. How do you perform this?
Yeah,
Is that your question?
exactly. Yeah.
Yeah. So I think that probably doing a loop is the best way to go about doing this. One of my action items for today is to develop a tutorial for this specific use case.
Mhm.
One of the constraints that you have when creating a filter based on the attributes is that you're limited by character count. So if you have a large number of objects, um, I I would recommend switching over to the JavaScript user-defined functions. Let me go ahead. I'm going to stop sharing my screen and pull up an example that I am working on but have not tested out. So um, maybe by the end of the day today, if you look at the GitHub user demos page, this will be updated. But let me go back to this. So in this cell here, um, I, if I increase the order to 29, for example, I'm my goodness, significantly going to increase the length of items in this array. And so to create the filter, I can use a JavaScript UDF and simply provide the list of arrays here. So, it may be useful to do a for loop to calculate all of the HealPix pixels associated with all of the objects that you're interested in, and then copy and paste the list of arrays to the template of this uh, JavaScript function. Does that answer your question?
Yeah, so I basically build the array with the pixels IDs instead of the coordinates.
Um, yes, but in order to build the pixels, you need the RA and deck.
Yeah, at the beginning.
Yeah,
Okay, I think I got it. Thank you, sir. Thanks,
of
Christopher.
course. All right. I think I can hand things over back to you, Melissa.
Yeah, looks like people are out of questions. So thank you, Chris. Thanks for being here, for making that presentation. That is great. I'm going to stop the recording.